actually going to present a lot of papers that will be persistent in the future. Is Yuanchao Xu. He is a fifth-year PhD student at NC State University, and he is interested about persistent memory and security stuff, and he is on job market for faculty position. So if you are potentially hire someone, feel free to reach out to him. But now the most important thing is that he is going to present the paper FFCCD. Take away.
Yeah, thank you for the introduction. I'm Yuanchao. I will introduce our work, fence-free crash-consistent concurrent defragmentation for the persistent memory. The persistent memory has provided many benefits, including the higher density, better addressable persistency, and the DRAM-like performance. But when we are enjoying those benefits, one problem is overlooked is about the persistent fragmentation. Let's see an example. So the persistent memory is organized as the persistent memory object tool. The internal memory allocator will manage the page and objects allocation within this pool. When the first process uses this pool, they may allocate the objects in a more compact way. And for the second process, it may allocate some new objects and deallocate some old ones. And the third process would also do the same thing. But afterwards, actually, what you can find is that the actual object size is significantly smaller than the memory footprint. So that leads to the memory fragmentation. And then the fragmentation would become persistent because the object lifetime would be larger than the process lifetime. So that leads to the persistent fragmentation. And that's the persistent fragmentation would get worsened with the subsequent usage. We are conducting the evaluation for the Redis. What we find is that after the first usage, the persistent fragmentation will reduce 25% throughput after the first usage. And one way to solve this problem is through the garbage collection, which basically include 3 steps. First two steps are the marking and summary. They will generate the GC metadata to decide which page should be compacted, and also like which objects should be moved to which place. And then during the compaction, it would start from the relocation. For example, that would copy the object 2 to the page 1. And afterwards, it also needs to update the corresponding metadata to indicate this step has been finished. And then that will need to update the corresponding reference to the new address to ensure the pointer will point to the correct location. And after that, the page 2 can be released to reduce the fragmentation. But if a crash happens in the middle, you may see the following state after the crash. So that means the GC thinks they already finished the relocation of these objects, but actually the object 2 has not been persisted in the page 2. So that would lead to the inconsistent states. So in this work, we're going to explore how to design the efficient and crash consistent GC for the persistent memory. This work makes the following contributions. First, we analyze the persistent memory fragmentation systematically to identify the S-fence as the key performance bottleneck. Then we analyze the post-crash states to explore the efficiency opportunities. And we designed multiple concurrent GC solutions, given that the stop-reward GC will have the long tail latency. And we designed the pure software solution which only need a single fence. And we also propose the architecture supported fence-free design. And we evaluate all of them to show their effectiveness. The following content would include the background, post-crash state exploration, architecture design, and evaluation. First, let's take a close look of the concurrent garbage collection. So it would start with the marking that will perform the reachability analysis from the root nodes to traverse the objects within the persistent memory pool. And after that, for the objects that cannot be reached, they are regarded as the memory leaks, and then they will be reclaimed. And during the summary, they will also generate the GC metadata to determine which page should be compacted and how they are compacting in the third step. And in the third step, that will first perform the object relocation and then the reference updates. In the first 2 steps, there's no crash consistency requirement because they will only extract some metadata from the memory allocation. But in the last step, that will require the crash consistency design because that will involve the object movement and the reference updates. If there's no crash consistency design, the application may not be able to resume the execution due to the garbage collection. And the concurrent compacting are actually implemented by using the read barriers. So as shown in this lines of code, the pointer P actually points to the object A. And then when you're trying to access the object A through this pointer, that will trigger a read barriers. In the read barrier, it will interact with the GC metadata to do the following checks and the relocation. First, it will check whether A is in a compacting page. If that is, that will look up the new address and also check whether A has been moved to the new address or not. If that has not been moved, so that will issue the mem copy to move this object and also update its state to indicate that has been finished, and also updates the corresponding reference afterwards. And a recent work explored the crash consistent concurrent GC in the S+ paper. So what they are doing is that they first persist the GC metadata before the compaction. And afterwards, in the read barrier implementation, they will insert two fences between the last three statements. And in that case, if a crash happens, they can simply inspect the moved state to see whether an object has finished its relocation. And then they can decide whether they need to redo it or not. But the problem is that this simple crash consistency design will, in its relocation, will incur more than 50% overhead of the total GC time. So what we are thinking is that whether we can remove those fences to improve its performance. First, let's take a look at the first fence. Actually, if we remove the first fence, the mem copy and the moved state update will be reordered. So that will lead to some post-crash inconsistent state. For example, that can be a partially moved state. That means the GC indicates this object has been finished, but the object only partially moved to the destination page. So that would lead to the inconsistent state. And when the object size is larger than one cache lines, that would lead to more possibilities which during if a crash happen. But when we analyze all the possibilities, actually there are several observations behind this. First, in either case, the mem copy source data is always clean. And the second, the reference are not updated, because as long as the reference is updated, so all the previous steps should be finished due to the second fence. And the third is that the memory copy destination value would be either the original value or the memory copy source. So that's leads to our first design is the single fence solution. So that means during the recovery, we can just compare the values with the memory copy source for the objects without the reference updates. If they are different, we will redo the mem copy and then update the moved states. If they are same, we just need to enforce the GC also record the same information. Then let's take a look whether we can remove the second fence. When we remove this one, that will lead to the numerous possible post-crash inconsistent states. That is because the read barrier already been passed. The application can write the new value to the destination page. So in that case, we analyze those inconsistent states and lead to the following observations. First is that the memory copy source would still be clean, but the reference may be updated. And the mem copy destination value would be either original or the mem copy source or the new value overwritten by the application. So that would actually complex our recovery step. So we are thinking about whether we can solve this issue from the third observation, which is that can we distinguish the original value from the new value such that we can decide whether we need to redo that step or just undo this step. If that is a new value or that is a mem copy source value, we can just redo other cache lines of these objects. And if they are the original value, we can just undo some side effects like the reference update. So to distinguish the original value to the new value, we are proposing the idea to track the relocated cache lines. That means the mem copy issued by the GC, we will tag those cache lines in the memory. And then if a crash occurs when these cache lines are in the volatile domain, we will our observation is that the reference may be updated and persist, but the application may write this cache line, but not persist yet. So that means the application do not expect to see the new value after if a crash happened at this moment. So that means we can just undo this step. We can just undo like the reference update and also the move state, such that this object relocation can be done just after the recovery process. And when the crash happened, when the tagged cache line reached the persistency domain, so we will like update that to the metadata to record this information. And then the reference may still be updated and persist, but the application may write and also persist this cache line. So that means we cannot redo that step. We must retain the current value that has reached the persistency domain. So during the recovery step, we can just redo other cache lines of this object to make it become a consistent state. So we propose the architecture support to implement our idea. The architecture design is the following: the memcopy in the GC will use the relocate instructions, which is the same as the move instructions, except that will add one more bit in those cache lines to indicate that are the cache lines are performing the relocation. And then when the cache line are evicted to the right pending queue, they will also carry this bit to the right pending queue. And we designed the rich bitmap buffer that are used. We propose the rich bitmap buffer such that the cache lines with this bit will update the corresponding entry in the bitmap. And meanwhile, if there's a miss happened in this buffer, that will retrieve the corresponding entry in the in-memory bitmap. And after if during the recovery process can just inspect this bitmap such that they can know whether this cache line has been like finished its relocation to the persistency domain, and then they can redo other cache lines of this object. So to optimize these read barriers, we already talked about how to like provide the fence-free design by optimizing the last three statements. And we also propose the design to like optimize the first three steps to further optimize its check and lookup step. But that will not be covered in this presentation. So our design summaries are the following. First, we provide the single fence design, which do not rely on any additional hardware support. Then we propose the fence-free design, which only need to add one more buffer at the memory controller side. And also we further optimize its check and lookup, which will add two more components in the CPU core. In the evaluation, we evaluate the PMM data structures and the PMM key value stores. For those workload, they will initialize with the 5 millionth insertion, and then we will delete 4 millionth node, insert 4 millionth node, and delete 4 millionth node again to simulate the peak and the low memory usage scenario in the real world applications. And in this figure, what we can see is that the default PMDK will have a much larger memory footprint than the actual data size. So that would lead to the fragmentation to reduce the performance. When we are adopting our method, actually that can reduce the fragmentation by 40% to mitigate this problem. And for the GC overhead breakdown from the left-hand side to the right-hand side, we are showing the baseline and the three designs we proposed. What we can find is that by using the fence-free design, that can reduce 62% overhead in the crash consistent data copy. And meanwhile, when we are adopting the defragmentation, that will improve the cache locality and reduce the TLB pressure. So that will also improve the overall performance. So the total execution time with the GC will only incurs about 4.1% overhead than the non-fragmented performance. In conclusion, we identified SFENs as the key challenges to design efficient crash consistent GC, and we proposed multiple solutions, including the software-only single fence solution and the hard architecture supported fence-free solution. And the FFCCD can reduce 28 to 73% of fragmentation reduction, and it incurs 4.1 runtimes overhead due to improving the application performance and low overhead from the GC. And that's all of this talk. Thank you for your attention, and I'm happy to take questions.
Questions from our audience? Okay, so I'm curious about if you have any insights regarding if your scheme is going to create any of the right amplification issues, given you might want to move stuff around differently.
That is actually maybe any the compacting reflection would create those right amplifications. So that means that will move the objects around and also update the reference accordingly. And there's some a software algorithm trying to reduce this right amplification. For example, only the long living objects will be relocated to some pages rather than relocate all the pages rather than considering all the objects aggressively.
Any other question from our audience? Okay, if not, let's thanks our speaker, and let's welcome the second speaker. Okay, so in the meantime, when she is setting up, you probably have to stop sharing your screen. Okay, so in the meantime that when the second speaker was setting up, let me introduce her. So Myoungsoo, no, what's the right pronunciation?
Miryeong.
Oh, Miryeong. Miryeong Kun, she is a fourth year PhD student at KAIST, and she is working with Myoungsoo, and she is interested in topics related to hardware software co-design, and she is presenting the paper LightPC. Well, okay, and well, she has to set up the Zoom. Okay, let's wait for a few seconds. Keep going, keep going. Yeah, 600 people using the same internet. That's true. Wait.
Can you close it and try to launch? Cancel. Now if you scroll down, join from your browser. Yeah. Okay. Type some join me.
Okay. Almost there.
Join audio by
So how many of you have ISCA 2022 as the first in-person conference since pandemic? Okay. How many of you have ISCA 2020 as your first ever in-person conference? Oh, welcome to ISCA. And how many of you are planning to attend any of the future in-person conference? Okay. How many of you feel comfortable about being in a crowd? Okay, less confident. How many of you plan to have dinner nearby tonight? Okay, how many of you still don't have any idea what to eat dinner? Okay, same here. All right. Are we ready?
Can you go back to this?
Okay.
Yeah, share screen. Go to window. Yeah, click the file and then share that.
It's probably easier if you just share the whole screen, I would say.
Exactly. What would you like to use? Oh, okay.
It's probably easier if you just share the whole screen because currently we don't see you sharing.
I think you'll have to share your host user.
You're not sharing.
Yeah. If you can go back to the browser.
How many of you know where's the next ISCA? You guys don't know? It's going to be in Orlando. How many of you think Orlando is more excited than New York City for ISCA? Yeah.
Please, okay. Can you go back? Can you go back?
What?
Try that again. Brand browser.
Yeah, it depends on my age, right? So if you like, I'm really young, so I love Orlando. And being honest to you, this is just my second time in New York City, but I've been in Orlando for probably 3 or 4 times. So definitely an evidence that I'm more for Orlando than New York.
Selected. Okay, so never mind. You can just share. We'll just give audio, like give the video back down.
Okay, so give it it's not long enough. You feel like you are a YouTuber now. Like sometimes YouTuber they would like Okay, sorry for people online. It takes a little bit of time, but sometimes waiting is worth it. So take it away. Well, audio.
Are we good? Are we good?
Okay, go ahead. Thank you, guys.
Okay. Hello, everyone. I'm Miryeong Kwon from KAIST, and my advisor is Myoungsoo Jung, who is Computer Architecture and Memory System Laboratory. Today, I'll introduce our work, which is LightPC, hardware and software co-design for energy-efficient full-system persistence, and this work is technically supported by memory. Before moving on to the main talk, I'll give you a high-level summary of the talk. Long-running applications require a robust system against system failures. That's why they use persistent mechanisms such as journaling and checkpointing. However, they degrade application performance a lot. PMM is suggested to replace the conventional persistent mechanisms to enjoy its 10 times larger capacity compared to DRAM and its non-volatile capabilities. However, it is hard to use because we have to modify the source code a lot and it shows non-deterministic latency. Thus, it's time to consider the easy-to-use non-volatile computing platform called LightPC. We also do the hardware prototype and achieve 4 times shorter execution time compared to the conventional persistent mechanisms. Let me explain more about our target research domain. Long-running application takes several months or several years for computation. For example, high-energy nuclear collisions take 6 months to be completed. However, machine failures are common in server-class computing domains. For example, IBM Blue Jeans mean time between failure is just 7 hours. Compared to 6 months, it is quite short. Thus, the persistent mechanism is required, and their goal is to turn the volatile states into non-volatile states. However, since they periodically flush the volatile states into the storage, they cause significant performance overhead. Thus, several studies try to leverage the persistent memory module to enjoy its non-volatile capabilities. And PMEM adopts the hybrid design. Data structures are stored in PMEM, while the execution flows, heap, and stack are stored in the DRAM. Because of the hybrid design, PMEM suffers from source code modification. First, we have to distinguish the DRAM and the PMEM device. Second, we need referencing method of non-volatile data structures. Last, we have to flush cache explicitly. Thus, PMEM is exposed as device file like div.docs 0.0. Then users map the device file into the memory address space via mmap. It allows CPU to load or store instruction to the PMEM device. Also, pointers of the non-volatile data structure should be self-contained in the PMEM space. For this, Intel provides PMDK APIs, and we can leverage the PMEM object create for object creation. Moreover, still there are volatile memories in the CPU, so we have to flush cache with self-flush instruction. Another challenge of PMEM is its varying and unpredictable latency that makes it unsuitable for working memory. The latency variation comes from its complicated internal architecture. And PMEM's architecture is complicated to support 3 types of devices, such as non-persistent working memory, non-volatile memory, and block storage. 3 devices require different access granularities. Its internal buffer is mainly used for bridging this disparity of data access granularity. Let me show you the memory access latency in the right side. Black is for DRAM, and then yellow is for bare metal PRAM. PRAM's read latency is similar to that of DRAM, while it exhibits 4 times lower latency for the write. Then what about DIMM level latency? Because of the repeated lookup whether data exists or not, the average read latency is 3 times worse than that of bare metal PRAM. In contrast to read, DIMM level write performance is 2 times to 6 times shorter than bare metal PRAM. It is because write requests can be absorbed by internal SRAM or DRAM inside of the PRAM devices. To sum up, there are 2 PMEM's limitations. First, PMEM's read latency is varying and non-deterministic. Second, we cannot avoid the source code modification and frequent cache flushes. In order to solve these 2 limitations, LightPC proposes hardware and software cooperative technique. Then now let's check how the hardware and software technique can solve the limitations. Our hardware solution is open channel PMEM, and it can make the PRAM latency deterministic. Since the internal volatile memories cause latency variation, we will remove them from the PMEM device. Then we will directly access the PRAM media by opening their channel to the CPU. Because of this open channel PMEM, we can enjoy DRAM-like read latency without performance variation. Then now we raise this question, what about the PRAM's low write latency? And let me answer this with our 2 insights. The first insight is that the load is dominant in workloads. When we calculate 17 server class applications, we observed 27 times more loads than stores. Furthermore, the cache hit ratio of the store is almost reaches to the 93%. The second insight is that although we have to access the PRAM media due to the cache misses, we can hide this long write latency. Because that burst time only takes 100 nanosecond to 10 microsecond, and long latency comes from the cooling down the PRAM server core, and we do not need to wait this time. In other words, if we only return write requests, we can hide the long write latency of PRAM. Next, let's check our software solution, which is persistent-centric operating system, which supports the transparent persistency. To achieve this score, first we remove the volatile and non-volatile boundaries, and we store all execution flows, heap, stack, and data structures on the parent media. Then how can PegOS handle the CPU's volatile memories? Actually, we leverage the power hold up time, and when power off, there is power inactivation delay, and the duration between the physical power off and 98% of nominal value is called power hold up time. And we measure it with the standard ATX and their solver, and we get the 22 millisecond and 55 millisecond for the power hold up time. However, as the ATX specification clarifies, the power holder time as 60 milliseconds, PegOS is designed by considering the worst case scenario. Then now, let me clarify the goal of PegOS. During the power holder time, it wants to automatically stop the computer time, like this image. And power on, PegOS can resume the computer time immediately without the booting procedure. Then I'll explain about the details of open channel PMEM design. OC PMEM consists of the persistent support module called PSM and bare NVDIMM. Bare NVDIMM can be designed as DRAM-like. DRAM puts 8 devices, and all devices are controlled by single chip-enabled signal. And since the access granularity of DRAM device is 8 byte, we can get the 64 byte from the DRAM DIMM. However, since the access granularity of PRAM device is larger than DRAM, if we design as DRAM-like, we will get 256 byte at once, which is not same with the cache line size. Thus, we designed the bare NVDIMM by making the group of PRAM devices. Two PRAM devices are controlled by same chip-enabled signal, and we can get the cache line size data. As there are 4 separated chip-enabled groups, we also can enjoy the intra-DIMM parallelism. And this can help PegOS to stop the computer time within the power hold time, which is 60 milliseconds. And the persistent support module is second component to OC PMEM, and it provides early return write. So when write request comes, PSM generates the write pulse to the target address and return the write earlier. By the way, this early return writes does not work for all scenarios. The first scenario is double write. If there is a write request to the early returned parent media, the write request cannot be served. And we have to wait until the thermal core cooling down. To solve this problem, there is a row buffer in the persistent support module, and the row buffer is used only for the store instruction and can absorb the double writes. Another critical scenario is read after write. So if a read request comes to parent media that is cooling down its thermal core, we have to wait as well. To solve this problem, we leverage the ECC data block. When one of the data block is involved in the write request, we can reconstruct the data block by XORing another data block and ECC block. And LightPC employs ECC hardware, which only takes 2.5% area of CPU and takes 1 cycle for encryption and decryption. So now let's putting it all together. PSM is connected to CPU via front side bus, and not only ECC, but also where labeling is performed for write requests. And where labeling algorithm is similar to start-get, which is simple but efficient. Furthermore, PSM provides flush instruction that does not allow the early return writes. Now I'll explain about the details of persistent-centric operating system. The simple concept of the PegOS is to flush the volatile state during the power hold-up time. However, simple cache flush does not work properly. In other words, although you thought that you stopped the computer time, someone ruined the time like this image. It is because there are multiple cores and even multiple processes. Let's suppose that core 0 tries to stop the time by flushing the caches. After that, core 1 can ruin that. Also, let's suppose that process A tries to stop the time, but process B can ruin at any time. Moreover, in the persistent support module, there are on-the-fly memory requests that we have to finish. To solve these problems, PegOS provides multi-step stop and go. The first question is, who manages this stop and go procedure? The answer is master core. When the power event signal triggers, the core handling that interrupt becomes the master, and it controls other slaves. Next question is where to store the stop time information. In the pyramid media, there are 3 types of control blocks for the process, device, and master. Then now let's check how to stop the LightPC platform. For the load balancing, master sends inter-process interrupt to slaves. Then all cores start to stop all the processes. Also stops all devices in the system and store their registers in the device control block. After that, all slave processors are stopped, and we have to keep the master information in the pyramid media. This is done by LightPC bootloader, and since the program counter of bootloader is stored in the machine exception program counter, we store the MEPC in the BCB as well. After the stop procedure, finally we stop the computer time like this image, and let's power on. Then MEPC is restored first, then the master processor can be resumed. When all the cores and devices are restored as well, the computer time is resumed. Before ending this talk, I'll show you our evaluation results and demo. We prototype LightPC hardware components using our custom system board to evaluate full system persistence, and PEG-OS is implemented on the hardware prototype. We also implement our own bare metal PRAM and also our own CPU. Here, I brought 2 representative evaluation results, and let's suppose we do not need persistent support. The white bar is for DRAM-only system, and blue bar is for bare and medium-only system. As shown in graph, LightPC only slows down 12% of application execution time compared to the DRAM-only system, which is reasonable to use it. And second, evaluation is when we need persistent support. Graph is relative performance of conventional persistent mechanism compared to our solution LightPC. And white bar is benchmark execution time, and gray bar is persistent control overhead. And as shown in graph, LightPC is 4 times faster than conventional persistent mechanism by eliminating the persistent control overhead. And let me show you our demo. LightPC performs the non-volatile computing. When power fails, it can guarantee the full system persistence. And here is the world's first bare metal PRAM-based non-volatile main memory and OCP-MEM enabled CPU, which is implemented on 28 nanometer FPGA. After loading FPGA file and persistent-centric operating system on our hardware prototype, we execute the program. If we suddenly turn off the program during its execution, what will happen? After a few seconds, we power on the hardware, and all program states are remained as before power failure, and we can re-execute it immediately without rebooting the operating system. So this is my concluded slide, and the proposed LightPC is our hardware software cooperative technique, and it guarantees full system persistence, both data and execution persistence. Our design is simple, brand new, and well harmonized with other emerging non-volatile memories, such as STT-MRAM, ReRAM, something like that. And we validate our system with hardware prototype by using the custom system board. And thank you for your listening. So if you have any question, freely ask me.
Question from our audience? Questions? Okay.
Hi, Ajay from MIT. I think this is a great talk. Can you just elaborate something on how would this work with some peripheral devices like GPUs, which are common in these server grade systems?
I couldn't.
Can you also make your system work for external devices like GPUs that have their own memory, or this is limited to only DRAM?
Actually, we are working on that. So I cannot explain more details about it, but we are considering about the GPU or another type of accelerator. Yeah,
Sure, thanks. I look forward to your paper.
thank you.
Other questions? Okay, so I do have a technical question. So I found your PAC operating system is kind of interesting, but I found there is potentially an issue that PAC operating system is heavily rely on the system to send out a signal to that the operating system knowing that it's a power failure state. But in many cases, when power failure occurs, there's no time, or it's just because something is broken, so we got power failure. And what if there's no such a signal being generated in your system while the whole framework is still working?
Maybe that is some flaws of our paper. Well, actually, our persistent network operating system really highly depends on the duration of power hold-up time. So really, if there's no power hold-up time, then maybe our system cannot work. But that is another. Maybe we have to find out another solution for that.
Yeah, I know it's difficult, but thanks for your honest feedback. And I think it's a great work.
Thank you.
Any other questions? Okay, if not, then thanks the speaker. And then we have our third speaker, Ahmed, and he is currently a senior engineer at Microsoft. Am I right? Okay. Yeah, it's difficult. Yeah, and his primary interest is in a general area of computer architecture, like many of us, and particularly have research interests in emerging non-volatile memory, storage systems.
Oh, 1 second. That's mine.
1 second,
Yep.
okay.
Yep.
And he got a PhD degree in computer engineering from UIUC and master degree from University of Wisconsin-Madison. And yeah.
That's all.
So slides. Since it's Microsoft, not to surprise, it's PowerPoint. All right, so ASAP as soon as possible. All right, cannot wait.
Thanks, Professor. So good afternoon. Thanks for attending our presentation today about ASAP, architecture support for asynchronous persistence. I'm Ahmed Abulila, and my co-authors are Professor Hajj, Professor Jung, and Professor Kim. So persistent memory refers to byte addressable non-volatile memory, whether it's a battery-backed DRAM, emerging non-volatile memory, or even a byte accessible SSD. Having persistent memory as part of the memory subsystem doesn't mean that the data can survive system crashes in a consistent state. An extra work is needed to support crash consistency. To achieve crash consistency, we need to support atomic durability in which a group of updates must be made persistent as a single atomic update. For example, inserting a node in a doubly linked list, we need to update 4 different pointers. The order of updating these pointers doesn't matter, but what matters is, in case of a failure, partial update without the capability of rolling back to a consistent state is not acceptable, which means all the updates within a single insertion need to be persistent atomically, all or none. So atomic durability requires first, the ability to control the order of persist operation, second, supporting data versioning. And we all know that. But when we think about multi-threaded applications running on systems with distributed memory systems, we need to ensure that we are not violating any control or data dependency between in-flight atomic regions as well. So let's quickly review the requirements for atomic durability. So ensuring atomicity can be achieved by both ordering persist operation and data versioning, as we mentioned. In data versioning, we make another consistent copy of the data persistent before updating the data itself. Here is an example. And for simplicity, I show here one of the 4 pointers updates in an atomic region for inserting a node in a doubly linked list. This approach uses the undo logging technique in which there are 3 main steps to ensure crash consistency. So the first step is a log persist operation. We save a consistent copy of the data in a log entry, then we make that log entry persistent. Second, we update the data. And the final step is a data persist operation in which we make the newly updated data persistent. If a crash happens in the middle of the operation, the recovery mechanism can use the log to retrieve the lost consistent copy of the data. With that, let's look at how hardware logging techniques handle control and data dependency. So here we have two threads. Each is executing an atomic region using a hardware undo logging technique that only commit atomic region synchronously. Let's focus first on thread 1. Thread 1 acquires a lock to protect its atomic region. Then we notify the hardware with the beginning of the atomic region. Once the hardware detects that the application is updating a persistent data within the atomic region, it initiates a log persist operation to save a consistent copy of the data before updating it. Then the hardware initiates a data persist operation after the log persist operation completes. Keep in mind, during the execution of the persist operation, the execution stalls. Once both operations are complete, the hardware safely commits the atomic region and thread 1 releases the lock. Meantime, thread 2 was waiting to acquire the lock, so it can now acquire the lock, then initiate its log and data persist operation. If a crash happens at any point of time, we can recover to a consistent state by rolling back the changes of any uncommitted atomic regions. On the other hand, if the hardware logging technique performs asynchronous commit while generating log and data persist operation in the background of execution, there is no guarantee that atomic regions will commit in the correct order, which is critical for crash consistency. Here, atomic region 2 commits before atomic region 1, even though there is a data dependency. In case of a crash, we may roll back the changes of atomic region 1, but not atomic region 2, violating the data dependency. So to avoid that problem, we must ensure atomic regions commit in the correct order without violating any dependency. We can ensure that by tracking dependency between atomic regions and enforcing the right order when commit. If a crash happens at any point of the execution, we will be able to recover the data back into a consistent state. And that's what ASAP offers. It has a hardware persist engine that initiates log and data persist operation in the background of execution. It has a dependency engine which tracks the dependencies between atomic regions. As a result, it commits atomic regions asynchronously while respecting any dependency. And it is ensuring crash consistency with low performance and area overhead. Let me explain main ASAP's hardware structure before showing an example. So we extended the process state with these state registers, which are initialized by calling a special instruction at the beginning of the application execution. They contain log registers that enable a hardware managed log. Also, there is a register to flatten nested atomic regions, and we have the current atomic region ID as well. These state registers enable an efficient support for context switching in the middle of executing an atomic region as well. So we extend the cache tags as well. We have the persistent bit that indicate if the data is marked as persistent or not. ASAP only initiate persist operation for data which is marked as persistent. Also, we have a log bit that assists ASAP in ordering log and data persist operation. ASAP needs to ensure that the log is made persistent before initiating the corresponding data persist operation. Finally, we have owner ID, which is the ID of the last atomic region that updated the data, and it helps ASAP to track dependency. The modified cache line list tracks the modified data in the L1 cache to avoid searching the whole cache to perform the outstanding persist operation. It has multiple entries to allow the execution of the thread to go beyond the atomic region boundaries and even start a new atomic region before the previous one commit. Finally, we have the dependency list that tracks all active atomic regions and any dependency that might exist among them. It facilitates the correct ordering of atomic region commits, and it's part of the persistent domain since its information is used in recovery. Now, let me show you how ASAP works using an example. Here we have an example of how ASAP handles two concurrent atomic regions running in two different cores with data dependence. Since the two atomic regions update the same shared data, a lock X is used to enforce isolation. And in this example, we show here the data cache for each thread. Within each cache, we show the data array, tag extension, and the modified cache line list. Also, we show the memory controller and the dependency list. So atomic region 1 has acquired the lock, and atomic region 2 has been initiated by calling ASAP begin instruction, which initialize an entry in the modified cache line list for R2 and an entry in the dependency list in the memory controller for R2 as well. R1 updates the location A, which sets the log bit that helps ASAP order log and data persist operation for A, sets the owner ID to R1, and it adds a pointer to A in the corresponding modified cache line list entry. Then ASAP initiate a log operation with the old value of A. The log persist operation for A has already persisted, and as a result, ASAP clears the log bit. After R1 update location B, a log persist operation for B is initiated, and its owner ID, log bit, and the pointer are set. When R1 reaches the end of the atomic region by executing the ASAP end instruction, the state in the modified cache line list entry is set to done, and ASAP continues processing any outstanding persist operation of R1. The data persist operation for A is initiated, but not for B, because the log bit of B is still set, waiting for the log persist operation of B to complete first. Execution continues past R1 on thread 1, while the log persist operation for B and the data persist operation for A are still in flight. This scenario demonstrates how ASAP performs persistent operation and commits atomic region asynchronously. The data persist operation for A and the log persist operation for B arrive at the right binding queue that removes the pointer for A and clears the log bit for B, allowing the data persist operation for B to be initiated. In the meantime, R2 has acquired the log X and updated A, which updates the data ownership to R2 and initiate a log persist operation for A. Additionally, since the cache line was previously owned by R1, R1 is added to R2 dependency list. One of the optimizations that ASAP enables is dropping the data persist operation when possible, which reduces the memory traffic to the persistent memory. Here, the log operation for A arrives at the right binding queue, and the right binding queue has the same data due to a previous data persist operation that causes the data persist operation for A to be dropped safely. Execution continue past R2 and on thread 2. Once its last data persist operation completes, R2 is marked done, impose the modified cache line list and the dependency list. However, it can't commit yet because it has dependency on R1, which hasn't been committed yet. When the data persist operation on B arrives at the right binding queue, it causes R1 to be marked as done in the dependency list. Since R1 has no dependency, it is safe to commit R1. R1 also broadcasts that it has completed, which clears R1 dependency in the dependency list entry of R2. Since R1 log persist operation are still in the memory controller, they can be dropped safely, and this is another type of memory optimization that ASAP enable. R2 may finally commit because its dependency are clear. Also, since R2's log persist operation are still in the memory controller, they can be dropped as well. So now let's take a look at the evaluation of ASAP. So in our simulation, we have used Gen 5 with the configuration shown here. All of our cores are accessing shared data, and we have several baselines such as software persistency, hardware undo logging persistency, and no persistency. No persistency doesn't enforce atomic durability, and it is intended to show the performance upper limit that we could achieve. So a SAB achieves a speed up of 2.1 over software persistency and 1.5 over hardware persistency, coming very close to idle performance. Idle performance is only 4% faster than a SAB on average. As for the memory persistent traffic, a SAB generates almost half the memory traffic generated by state-of-the-art techniques. And that is mainly due to overlapping the persist operation with the execution, which allow different memory traffic optimization techniques to be more effective. To study the sensitivity to slower persistent memories, we conducted experiment where the latency of accessing persistent memory is varied from 1 to 16 times the battery-backed DRAM access latency. The throughput here is normalized to the non-persistent case running on the battery-backed DRAM. Overall, a SAB has much higher throughput than the state-of-the-art approach with a sensitivity that is closer to the idle case. In conclusion, a SAB is an optimized hardware undo logging technique that commits atomic regions asynchronously while enforcing any control or data dependency. A SAB significantly reduces the idle time and the memory traffic compared to the state-of-the-art techniques. That's all I have for today's presentation, and you can find more information in the paper. Thank you.
Any question from our audience? Okay.
Hello, my name is Antonis Psistakis, also from UIUC. So a question I have is, can a SAB be used to achieve asynchronous persistence across nodes? And what would be needed to be added, or what is your opinion on this?
Could you repeat the question?
Yeah, can we use, or how someone could use a SAB, the scheme of a SAB, for asynchronous persistence across nodes? So not only among threads, but across different computing nodes.
So now we will not have like a fixed latency for all the requests. There will be variation, and as we have shown here, the sensitivity to latency is good for a SAB. So I believe it will work, but we didn't evaluate such configuration. Yep.
Hi, I'm Gil. Yeah, I was wondering, your code examples for code using persistence all had a single lock covering the whole thing. If someone were to write code using multiple locks or improperly not using locks, is it possible to get cyclic dependencies among the...
Yes, and this is something that we mentioned in the paper. You can't have like multiple critical sections in your atomic region. This might cause what you just mentioned, circular dependency.
Okay.
Yep. And I believe this is shared also with other hardware techniques, this limitation.
All right. If we don't see any other question, let's thank the speaker. All right. So in the meantime, during the transition, I want to interview two guys. What's your name?
I'm Kumar.
And
Cambridge. I'm Cambridge.
Okay, so one thing I do want to say, thank you guys. You did an amazing job in helping the in-person session here as well as the online session. So let's give them an applause. And our first speaker, not ready yet. how to pronounce your name?
You can just say Gagan.
Gagan, okay, Gagan, he is a postdoc at UTH Zurich in Safari Research Group. In March 2021, he received his PhD degree from TU Eindhoven, Netherlands, and in collaboration with IBM Research Zurich under the supervision of Professor Oner Mutlu and Professor Henk Koppero. And he is passionate about computer architecture, machine learning, and hardware acceleration. And please take away.
Thank you very much for the introduction. First of all, thank you everyone for staying until this long. Today I'll present Sibyl, which is an adaptive and extensible data placement in hybrid storage system using online reinforcement learning. First, I'm going to give an executive summary. Hybrid storage systems use multiple different storage devices to provide high and scalable storage capacity at high performance. We observe two key shortcomings of prior data placement policies. First is the lack of adaptivity to both workload changes and changes in device types and configurations. And second is the lack of extensibility to more devices. So our goal in this work is to design a data placement technique that provides adaptivity by continuously learning and adapting to the application and underlying device characteristics, and also provides easy extensibility to incorporate a wide range of hybrid storage configurations. To this end, we contribute Sibyl, which is the first reinforcement learning-based data placement technique in hybrid storage system that provides both adaptivity and easy extensibility, and also provides ease of design and implementation. We extensively evaluate Sibyl on real systems using a wide range of workloads. We show that Sibyl outperforms state-of-the-art techniques by 21.6% on dual hybrid storage systems. And in a tri-hybrid configuration, Sibyl outperforms the state-of-the-art policies by 48.2%. And Sibyl is able to achieve 80% of the performance of an Oracle with storage overheads of only 124.4 kilobytes. We will open source our source code on our GitHub repository. This is the outline of my talk. First, I'm going to start by discussing the key shortcomings of prior data placement techniques. Let's look at some of the basics of hybrid storage systems. Over here, we have a typical hybrid storage system consisting of a fast yet small storage device and a slow yet large storage device. The address space is divided into a number of logical blocks, which are assigned to an applications. The storage management layer here is responsible for the orchestration of host input-output requests across heterogeneous devices. It also manages the promotion and eviction of data from the fast and the slow devices. So a desirable policy has to effectively utilize the low latency characteristics of the fast device while making an optimal use of its small capacity, and should also provide easy extensibility to wide range of workloads. And a different hybrid storage system configuration as well. Therefore, the performance of a hybrid storage system highly depends on the ability of the storage management layer to effectively manage diverse devices and workloads. We observed two key shortcomings in the prior data placement techniques that significantly limit their performance. First is the lack of adaptivity to workload changes, and also the changes in device types and configuration. Second is the lack of extensibility to more devices. Let's take a closer look at each of these shortcomings. First, past techniques lack adaptivity to workload changes because they only consider a limited number of workload characteristics, and which are statically tuned. And the designer expects that these characteristics are going to work for all the dynamic workloads. Over here, we show average request latency of 4 sample workloads, and also the average across all the different workloads we evaluated for a CDE policy, which is a state-of-the-art heuristic-based policy. And we also show RN and HSS policy, which is a supervised learning technique. And we compare these policies to an impractical Oracle, which has knowledge of future input-output excess patterns. So we can't be better than this. So the lower the request latency, the better. We observe that like all the baseline policies provide some reasonable performance under specific workloads, while for other, they show way lower performance than Oracle. And on average, we observe a performance loss for some policy by 41.1% compared to an Oracle. We conclude that considering only a limited number of workload characteristics leads to a significant performance gap. And also these techniques lack adaptivity to device types and configurations because they do not consider the underlying storage device characteristics. Over here, we again show the three policies, but we also have another extreme case where we place everything in the slow memory, which is we refer to as the slow only. We observe that the performance of some workloads is even worse than slow only policy that places everything in the slow storage. While in another configuration of a hybrid storage system, we observe that these workloads are able to perform better than the slow only policy. Therefore, we conclude that high diversity in device characteristics makes it really difficult to make one generic policy which will work for all different configurations. And the second key shortcoming is that most of the prior techniques are rigid. They require significant effort to accommodate more than two devices. For example, if we extend a dual hybrid storage configuration to a tri-hybrid configuration, then we would have to redesign a new policy to handle all the different scenarios which will come up, for example, for promotion, for eviction. So that's why you spend a lot of designer effort and waste a lot of precious time and resources. So our goal in this work is to design a data placement technique that provides adaptivity by continuously learning and adapting to both the application and the underlying device characteristics, and also easy extensibility to incorporate a wide range of hybrid storage configuration. So to this end, our proposal is Sibyl, which formulates data placement in hybrid storage system as a reinforcement learning problem. Let's go into the formulation of data placement as a reinforcement learning problem. First, I'll briefly describe what is reinforcement learning. In reinforcement learning, it consists of two important components. First is the agent and the environment. The agent observes the state of the environment, and in every time step, it takes an action based on the state. And for every action, it receives a numerical reward, which is kind of a feedback from the environment to tell how the agent is performing. The agent's goal is to find a policy where agent's action in a given state leads to the maximization of the reward, and which eventually becomes the agent's policy. So if you look at the formulation of data placement as a reinforcement learning problem, we have the agent, which is Sibyl, and it's observing the environment, which in our case is the hybrid storage system. And the agent for every storage request looks at the feature of the current request and also the system condition. And based on these state, it takes an action. In our case, the action is to where to place the current request. And then the hybrid storage system provides a feedback to evaluate the effectiveness of the data placement decision. And now we will concretely define the state action and the reward for Sibyl. First, for the state, we use limited number of state features after performing feature selection. First of all, to reduce the implementation overhead. And secondly, we observe that RL agent is more sensitive towards the reward. So therefore, like adding more states doesn't really help. And therefore, we choose a 6-dimensional vector of state features, which has, for example, the size of request, the type of request, etc. And we also quantize the state representation into small bins to reduce the state overhead, because you will need like a bigger state vector for that. And then we define the reward. The reward is the objective of Sibyl. Though Sibyl can learn from any different sort of reward, but in this paper, we formulate the reward as a function of the request latency. And this, in our reward, encapsulates 3 important aspects. First is the internal state of the device. For example, the read-write latency, whether there is garbage collection or queuing delays. And also it encapsulates the throughput as well, and amount of evictions that are happening from the slow device. We provide more details on each of these aspects in the paper. For the action, we define the action as the selection of a storage device to place the current page. Such an action allows us to easily extend our framework to any number of storage devices. And also we observe that it makes Sibyl learn to proactively evict or promote a page from the fastest storage device. We now provide a brief overview and design of Sibyl. First, we discuss the execution model for Sibyl. We implement Sibyl in the host OS, where for every storage request, Sibyl uses an RL decision thread to make data placement decisions. Sibyl uses another thread, which is called the RL training thread, which runs in the background. It keeps collecting information about the Sibyl state, action, and reward, which it uses to train a data placement policy in the background. And periodically, we replace the RL decision thread policy with the RL training thread policy. Our two-threaded implementation allows us to run we run it asynchronously, which avoids the training in the RL training thread interrupts or delays the data placement decisions for the incoming request. Now we'll go into the implementation of each of the thread. First, we discuss the RL decision thread, as I mentioned before, where Sibyl decides the data placement of the current storage request, and also it keeps collecting information about its decisions. For every new storage request to the hybrid storage system, Sibyl uses the state information to make a data placement action. We have an inference network that predicts the expected benefits of each of the given state. And then the Sibyl policy selects the action with the highest expected benefit, or a random action for exploration of the hybrid storage system, so that we do a trade-off between exploration and exploitation. While making the data placement decision, Sibyl collects the information about the states, action, and rewards in an experience buffer, which is used in the RL training thread. In the RL training thread, Sibyl uses these collected experiences to update its decision-making policy online by training a separate neural network. Therefore, Sibyl continuously learns from its past decisions and their impact and their actions. To enable the parallel execution of these two threads, we duplicate the neural network that is used to make the data placement decision. So the inference network does not have a separate training step, and we only transfer the weights from the training network periodically to the inference network, which allows us to keep the data placement out of the critical path. We now present some of our key results. We perform real system evaluation for both dual hybrid and tri-hybrid systems. Over here, we show our evaluation setup, which consists of multiple different devices. We implement Sibyl in the storage management layer of an AMD Ryzen 7 CPU. First, we evaluate for a dual configuration, we evaluate a cost-oriented hybrid storage configuration in which we use a high-end SSD, which is connected to a low-end hard disk drive, where the latency difference between the two devices is quite large. So it's optimized for the cost. And second, we try a performance-oriented hybrid storage configuration, where we use a high-end SSD with a middle-end SSD, where the two devices have similar latencies. We use 18 different workloads from MSR Cambridge and File Benchmarks feed and compare Sibyl against four state-of-the-art policies, which consist of 2 heuristic-based policies and 2 supervised learning-based policies. So over here, we show the performance results in terms of average request latency for all the MSR Cambridge workloads for all the different policies we consider. Over here, we also have the Oracle policy. And we observe that Sibyl consistently outperforms all the baselines for all the workloads. And in the performance-oriented hybrid storage configuration, where the two devices have similar latency, Sibyl provides 21.6% performance improvement by dynamically adapting its data placement policy. However, we observe like Sibyl provides slightly lower performance than other baseline policies in 2 of the workloads for this specific configuration. And we observe that these workloads are write intensive and have many random requests in terms of both excess pattern and request size. Therefore, in the paper, we show that for such a workload, we need to perform frequent retraining and also the transferring of weights from the training network to the inference network. However, on average, Sibyl achieves 80% of the performance of an Oracle policy that has complete knowledge of the future excess patterns. We also evaluate the extensibility of Sibyl to more devices. As I mentioned, to extend it to a tri-hybrid system, we had to only add a new action in the action space and add the remaining capacity of the new device as the state feature. That's it. And Sibyl was able to figure out the policy on its own. However, we have a heuristic-based policy over here, which is an extension of the previously shown the CDE policy, where we had to do a lot of effort to extend it. Because you have to handle all the different cases about when the eviction happens and the promotion happens, and you also need to figure out all the heuristic parameters, so you need to set those things. So however, in this case, we just left Sibyl to decide what is the best policy. And in the end, we observed that Sibyl outperformed this state-of-the-art data placement policy by 48.2% in a real tri-hybrid system. So we conclude Sibyl reduces the system architect's burden by providing ease of extensibility. All of the Sybyl's performance benefits comes at a modest cost of 124.4 kilobytes for the storage, which we need to implement the experience buffer to keep all the experiences. And also we use a really small network for inference and training network. So it's not really big. And we need 40 bits metadata overhead per page for state features. And the inference latency is only 10 nanoseconds, which is actually orders of magnitude lower than the input output read latency of an even high-end SSD. If to give you an example, if you think about the Samsung Z9 has a 3 microseconds latency. And for the training, we need 2 microseconds. However, like as I mentioned before, training and inference happen asynchronously, and the training happens in the background, so it's not really in the critical path anymore. So Sibyl provides small area overhead and small inference overhead as well, and is able to satisfy the prediction latency. We have many more exciting results in the paper, including the throughput evaluation, the evaluation on unseen workloads, and on mixed workloads as well. So for more details, I encourage you to read our paper. Now I will conclude my talk. We introduced Sibyl, the first reinforcement learning-based data placement in hybrid storage systems that provide adaptivity and easy extensibility, and also ease of design and implementation. We evaluated Sibyl on real systems using many different workloads. Sibyl improves performance by 21.6% compared to the best prior data placement policy in a dual hybrid storage system. And in a tri-hybrid system, Sibyl outperforms state-of-the-art policy by 48.2%. Sibyl is able to achieve 80% of the performance of an Oracle policy with a storage overhead of only 24.4%. We'll open source our code on our GitHub repository. Thank you very much. I'll be happy to take any questions.
Okay, hi, this is Daniel Berger from Microsoft. We tried a similar approach in 2018. There's a couple papers in the systems community that seem relevant. And one thing we experienced there is that the feedback cycle is too long.
Right.
How did you, so our feedback, we got usually a feedback as in an access to a page on the fast device every week. So you learn on the cycle of weeks. And so then you need a couple million weeks to learn. How do you overcome that in your case?
So what sort of system were you using in that case? Or?
A storage system for a content delivery network.
Okay. Because in our case, like we were getting, it was not really like every time instant, but we got it like after a few seconds because we had like this, if you saw the picture of the configuration, it was a desktop like system. So we were able to get the feedback like quite early, but I don't know if it's a cloud system or a different system. Maybe there could be an issue in terms of like when you get the feedback. Yeah, for us, it was few seconds.
Maybe you should try on a bigger system.
Oh yeah, for sure. Yeah. Oh, thank you.
Other questions?
Hi, so this is Miryeong from UC Davis. So I remember that you mentioned about like oral decision making threads and things like that. So my first question is that who is responsible for all of those computation? And also in your overhead slides, I didn't see anything related to their overhead, like computational overhead for the RL related computation that you need to handle all of these things. Have you ever considered the computational overhead for your system, for your framework?
Right, we had the overhead in terms of the inference, right? For the inference and also for the training of RL, these models. So.
Oh, okay, so you refer to 2 microsecond?
Right.
Okay.
And everything is implemented in the kernel, the Linux itself. And so we take, and everything is on the software side. So we didn't really do like anything on the hardware or GPU side because first we were thinking about doing it on the GPU side, but then you have to do these transfers between the GPU and over the PCIe. And also we were not using like super big networks. And so we didn't really want to, for everything, send data over the GPU. So we did everything on the software side and we were able to satisfy the latency, at least for our use case, which we were considering.
Okay.
Yeah.
Thank you.
Thanks.
Other questions? All right. If not, thanks to all the speakers of this session and thanks to all of you staying here. There's still another session going on. If you are interested, you can plug into the other session. Otherwise, I will see you tomorrow.